Are people still entering, or can I start?
You can start.
Okay. Good morning, everybody. Welcome to this webinar organized under the wings of Water Europe. My name is Charlotte Boeckaert. I am the leader of the expert group Water and Agrifood. And today we want to welcome you in the world of the digital tools and decision support systems for water management in agriculture. So this is the agenda for today. I will first give the floor to Andrea Rubini, who is the Director of Operations of Water Europe. And after his introduction, we will have 4 more technical talks about digital tools and decision support systems. And after that, we will close with some concluding remarks. Just some practical information before we head off. If you have a question for one of the speakers, feel free to put your question in the chat. If time allows, we will handle your question after each presentation, or we will do it at the end of the different presentations. Perhaps you might be aware of another useful tool for water management in agriculture. You know it, or you develop some tools yourselves, then we are very much interested to know more about it. So we have generated a small information sheet, which you can find already in the chat. Feel free to fill it in and to mail it back to me, and then I will make sure that all attendants of this webinar get a compilation of all the completed information sheets. After the webinar, we will share the slides and the info sheets with everybody. And just to tell you that we also intend to organize 2 more webinars related to water and agri-food in the course of 2026. So with that, I want to conclude my short introduction, and I give the floor to Andrea Rubini.
Thank you so much, Charlotte. Thank you for the introduction. And good morning, everybody, and thank you for joining the webinar of today. Let me also share my screen. I have quite a short presentation to share with you, with the audience. The webinar today on digital solution and decision support system for water management in agriculture is really a pleasure to introduce this session on behalf of Water Europe and to really frame, our discussion around the work of the Water and Agri-Food Expert Group of Water Europe and with a touch, on the EU water resilience strategy and agenda, because as you know, this is becoming the main driver in the water environment. So let me go to the next slide. As many of you, I hope that many of you know, Water Europe is a multi-stakeholder forum, so a platform that brings together around 300 organizations that covers the entire value chain of the water sector. The structure of Water Europe revolves around expert groups, they act as technical communities of practice that are dedicated to advancing the knowledge, the sharing, and the shaping of research and innovation priorities, and supporting the transition towards what we call a water smart society and economy. Expert groups of Water Europe are really essential collaboration areas, spaces where expertise, innovation, and policy can meet in a collaborative environment. So this is you can see the Water Vision 2023 of Water Europe, in which you can see that our approach is really to forward, to progress, to advance for a water smart society in which the value of water is fully recognized and realized in order to ensure that water is secure, sustainable, and resilient. And the last word, is the one that connects to the European Water Resilience Strategy, which is for which I will give you some information in few minutes. So, as you can see, our action aims at working in order that water scarcity and pollution are absolutely avoided, that the resources, water resource loops are closed in order to foster this welcome and needed circular economy, and then also that all the water systems are resilient against the impact of climate change, and of course also demographic change, which is an important factor in the water resilience. And of course, we need also to work on efficient water governance in order that we can put together an inclusive water governance system. Water Europe organization is made of three main programs: advocacy, collaboration, and implementation, and three main pillars about communication, the community, because it is a community-based organization, and projects. Now we go to the expert groups. As you can see, the expert groups are organized in Water Europe and cover all the major dimensions of water. It's from water security, resilience, and digitalization to circularity, governance, biodiversity, and health and human resources. The Water and Agrifood expert group plays a particular important strategic role because I can imagine agriculture represents the highest share of water use in Europe, and at the same time, one of the sectors where the innovation and smarter resource management can generate the greatest impact. The expert group, it is led by Charlotte Boeckaert, so co-led by Antonio Lorenzo, and as a special advisor in Jochen Frerich. What is important to say? About the water resilience strategy. The water resilience strategy was published by the Commission early June 2025. It is made of three building blocks, as you can see from this slide. One is about restoring and protecting the water cycle, building a water smart economy, and we say also society, and to ensure clean and affordable water and sanitation for all. These are the three main blocks of the strategy, which are quite important because if you go, for instance, to the map of restoring and protecting the water cycle, you see that here we have important topics at stake. On the one hand, we have the existing legislation for fresh water that needs to be implemented in a better way. The prevention of pollution at source, and particularly concerning now, the emerging or eternal contaminants like the PFAS and other persistent chemicals, and strengthening the source to sea links, because whatever goes to the sea starts from the inland water, which of course includes also the matter that we need to work on water retention and enable our cities and landscape to be more efficient in water management. The block 3, building a water smart economy. Of course, the recommendation is about water efficiency, enhancing the capacity of the water industry to be being competitive not only in Europe but beyond Europe. And the enhanced water efficiency means across all sectors in a synergic and systemic way. About the ensuring clean and affordable water and sanitation for all, this is also makes reference to the relevant SDGs, but in the same time in this block, the water resilience strategy looks at capacity of increased consumer awareness, which can be translated in more water literacy from the civil society, the implementation of the most important directives, city planning. This also connected to the new European Bauhaus that seems to have quite an important framework in the next MFF of the European Union, and the support to exchange best practices across water pricing policy, which is quite a sensitive issue. So as you can see, then we have 5 enabling areas in the water resilience strategy. I go very quick: governance, implementation, finance, investment, and infrastructure, because we go nowhere without a relevant and important and efficient finance, investment, infrastructure in the water sector. We need to push on digitalization as much as possible. We must be prepared, for early warning system and critical entities resilience directive. And of course, I mean, our attention also from the Water Europe, from the collaboration point of view and the expert group for Water Europe, it is a lot on innovation, research, innovation, industry, and skills. In terms of state of the affair, well, I mean, let's say there will be an EU water research and innovation strategy, which is connected to the water resilience strategy. As you can see, I mean, one of the point, or like, I mean, really to highlight the matter that it is important to connect the mission ocean and waters in order to connect both the strategies. And what is important is also that to highlight the matter that the concept from source to sea will be fully exploded, I mean, in the next development of the strategy. So now, in terms of there are two roads. I mean, towards the water research, resilience, research and innovation strategy. You're going to have, I mean, more problem identification in terms of innovation needs, to push more on solution opportunities, including the matter that there's a need for better deployment, enhancing the knowledge gap definition, and resulting in this also in more needs and action in research and innovation. Just mentioned the matter that water resilience strategy mentioned also the creation of the European Union Water Academy, which aims also at supporting, I mean, skills development in Europe, and of course prioritization of research and innovation action in order to have, I mean, more correspondence for the next multi-annual planning. In terms of development process, in terms of consultation, the call for evidence tentatively launch will be mid-December 2025, so we are waiting for that. At the same time, stakeholders have been already involved in two sessions, one the 16th October, the second time on the 21st of November, and on the 4th March, during the mission Ocean Forum 2026 that will take in Brussels, there will be the presentation of the results of the call of evidence and the results from the various consultations activities. That's all from my side. I hope that you enjoyed, I mean, this presentation, and I'm confident that there will be a lot of insights and inputs that will come from the different speakers. And I take the opportunity to give the floor to Dorina Bogdani, and that she will continue this webinar. Thank you so much, Dorina.
Thank you very much, Andrea, for your introduction. So hello, everyone. My name is Dorina Bogdani, and I'm an agricultural engineer at AGENSO. Today, I will present you a general introduction of data collection, data analysis, and decision support system in agriculture, and how these technologies are transforming farming. So, wait a second. Digitalization has become essential for the agricultural sector. Farmers today face major challenges: climate change, unpredictable weather, resource limitations, and increasing production demands. Studies show impacts regarding climate change, such as sea level rise, ocean acidification, and many others, affect crop development, reduce yields, and make farming more unpredictable. As crops become stressed, we see impacts on prices, volumes, and quality. In 2018, over 820 million people worldwide face malnutrition, and climate change is expected to worsen food security. This makes it clear why digitalization is crucial. We need better tools to monitor the environment, predict the risks, optimize resources, and support farmers in adapting to these challenges. Agriculture is becoming more complex than ever. Climate change, resource scarcity, and market pressures require farmers to act smarter and faster. They need timely and accurate information, and digital tools can provide exactly that. Today, we see a growing use of farm management software, remote sensing, and decision support tools. Additionally, there is an increase in EU funding that supports digital transformation in agriculture, making these technologies more accessible. To start analyzing digital tools, we need to start from the beginning, which is data collection. What is data collection? Data collection refers to gathering information about all aspects of farming, crop health, soil conditions, weather resources, and day-to-day operations. Why is it important? Because better data leads to better decisions. When farmers have accurate and frequent data with good coverage of their fields, they can optimize crop yields, use inputs more efficiently, and follow a more sustainable future or practices. Agricultural data can come from many sources, including remote sensing and satellite imagery for crop monitoring, weather and environmental stations, field sensors measuring moisture, temperature, and nutrients, and lastly, farm management records such as planting dates, fertilizer use, irrigation schedules, and harvest yields. All these data streams can help build a complete picture of what is happening in the field. Once we collect the data, the next step is data analysis. This involves using AI, machine learning, and statistical models to extract useful insights. Through data analysis, we can understand trends, detect problems early, and make predictions. Key applications include precision farming, predictive analytics, such as forecasting yields or irrigation needs, crop and soil monitoring, livestock management, and finally, descriptive analysis to summarize field conditions. This makes farm management more efficient, profitable, and sustainable. Combining data collection and data analysis, we get decision support systems. Decision support system, or DSS, take the analyzed data and turn it into actionable recommendations. They help farmers choose the best moment to irrigate, fertilize, or harvest, amongst other recommendations, improving both productivity and sustainability. Decision support systems provide a wide range of benefits. Better resource management, like optimizing irrigation and reducing water waste, improved fertilization timing, reducing input use and costs, smarter pest management based on weather and climate data, accurate harvest planning to improve yield quality, risk assessment, helping farmers anticipate climate-related threats, and lower operational costs and labor needs through optimized field operations. A question that often forms when talking about digitalization is how automation is shaping the future of agriculture. Automation is shaping the future of farming by increasing accuracy through data-driven operations, reducing human errors, lowering operational costs, improving efficiency and coordination, and in conclusion, it reduces the need for manual labor, allowing farmers to focus on higher value tasks. Now let's take a look at a real example, which is RWC.gr, created by AGENSO. This case focuses on smart irrigation and water management, an area where digital tools can make a significant impact. Every solution created has a problem that needs solving. In this case, the problem is that around 70% of total water consumption is used in agriculture. Combined with current water scarcity, this creates a serious need for innovative solutions to manage irrigation more efficiently. The solution is an integrated irrigation tool that supports real-time monitoring and precise irrigation. Using a web app, the system calculates the optimal amount of water needed based on crop requirements. It can also fully automate the irrigation process, making it easier for farmers to save water and reduce costs. This system offers several innovative features: plug-and-play installation, small size and energy autonomy, support for multiple sensors, full automation and remote control, use of alternative water sources, and at last, calculation of optimal irrigation quantity. Overall, it helps reduce production costs and improve both yield, quantity, and quality. As for the sensors, It supports weather stations, water quality and quality sensors, and energy meters, flow meters, and manometers, amongst others. As for actuators, it includes relays and electrovalves for automating electrical and hydraulic circuits. This integrated system comes with a web platform with no subscriptions or additional costs. The web application provides data visualization, automatic calculation of irrigation timing and dosage, personalized notifications, weather forecasts, creation and activation of automations, and last but not least, remote control of electrovalves or pumps. This gives farmers full control from everywhere, as it does not require internet connection. The system comes with an integrated SIM card, so there won't be no connectivity problems. This technology is already being applied in agricultural production, such as vineyards, apple orchards, etc. Also in circular water economy systems using rainwater for irrigation applied in islands here in Greece with problems concerning droughts. Moreover, in urban gardens using principles of circular water economy, as well as in water and energy management in field industries like Italy, Spain, Greece, and Ireland through the Axel Water project. And additionally, the system can serve as a flood assessment, a prediction tool, and is currently installed at key locations throughout the municipality of Trikala. The municipality of Trikala has also used their systems for the automated control of public lighting. And finally, this innovative and integrated solution has been deployed in several remote areas. The photo shown was taken at the highest peak of Mount Panassos. As you can see, the system operates reliably, even under extreme conditions, without experiencing any connectivity issue. This shows how important it is to have data from every aspect of the field, of farm, of anything that you want to control. Thank you very much for your attention, and I'll be happy to answer any questions if I'm on time.
Yes, thank you, Dorina. I don't see questions yet appearing in the chat, but feel free to do so. In the meanwhile, I will hand over the word to our next speaker, which is Vito. So Vito, please go ahead to share your screen and give your presentation. Thank you.
Okay, thank you. Can you see the screen?
Yes, but not yet in full presentation mode.
Okay, sorry.
Yes, now we see it in full presentation. Yeah.
Okay, okay. Now it works.
Yes, indeed.
Okay, thank you. This is Vito Buono from Sysman. First, thanks to the organizer for the invitation. I just want to clarify, I'm not a researcher, I'm a technician, and this is not a commercial presentation. My goal will be to share my experience from the perspective of a field technician, the head of research and development of our platform, which is Blueleaf DSS, providing some technical support to end users. So this is my main job. And the hope is to provide useful information about the main issues and experiences that we have for the practical application of what we call DSS at field scale. So a very, very quick look to DSS, Blueleaf DSS, which comes from originally a local project started more than 10 years ago. It is a digital platform based on cloud technologies, available in web and app versions for farmers, industries, technicians, and researchers. We provide a lot of tools and different technologies related with the type of application that you can see on the screen. We will focus today on the irrigation scheduling, but we cover very, very different issues from the field to the farm to the chain and district scale. So let's a bit of introduction on scientific approaches for irrigation scheduling, because we are supposed to discuss about this. DSS for irrigation scheduling should support the daily irrigation scheduling of the farmer, and relating to the crop type, the weather condition, the soil parameters, and the irrigation system parameters. The scheduling should be provided in order to avoid both excessive saturation or water deficit, and also taking care of the crop quality and phytosanitary status of the crop. DSS should also support the farmer to adapt to climate change, water scarcity, and other environmental concerns. And finally, as already was mentioned, DSS should also integrate with remote control system for irrigation and fertirrigation. The main scientific approaches that are available to do so is that DSS can be based on plant water sensor. For example, we have some examples here that has some advantages because they measure directly the plant water status and the response, and they integrate somehow environmental effects, but they have some disadvantages. They don't provide information about how much water to provide, for example, and the most of them need calibration, and the most of them are still at a research scale. Commonly, DSS are based on soil water sensor. Also here, there are a lot of also commercial solutions. They are relatively easy to apply. They have a good precision. They can inform about how much water to apply, but as a disadvantage, they are difficult to apply in very heterogeneous soils. They don't consider the evaporative demand of the atmosphere, and sometimes they require a soil-specific calibration. The final approach could be to use modeling. There are different types of approaches based on modeling. The advantage is that they integrate climatic data and they are relatively easy to apply. They inform about when and how much water to apply, but they require good measurements of local weather variables and a good setting of model parameters. Given these advantages and disadvantages, our approach was to integrate the whole of them. So starting from DSS inputs like weather data, model parameters, and user inputs, we use modeling to schedule day-by-day irrigation, providing information like crop evapotranspiration, soil water depletion, and irrigation scheduling. And we use remote or proximal sensing in a closed loop to monitor the crop soil water status and to understand if our scheduling is creating excess or deficit in the water status of the system. The crop water balance model is based typically on the FAO irrigation and drainage approaches. So we have based, like a lot of solutions available on the market, our algorithms based on this basic modeling. And somehow we have adapted the modeling in relation to specific type of cropping system. And so the software provides day by day the estimation of the reference and crop evapotranspiration, and so the irrigation advice, the status of the soil water content, and so the soil water balance of the crop, and the irrigation scheduling, and with all the components related with irrigation scheduling. And this can be viewed by the user with a friendly app on the mobile phone. So as I mentioned in the introduction, my goal is to share something related with the variables and parameters that we require to perform DSS for irrigation, and what are the issues at field scale to manage the complex list of variables and parameters that are required, as you can see in this table. Let's start from the weather variables. It has been mentioned that we need good weather data, so solar radiation, temperature, relative humidity, wind speed, and rainfall, and some correction factors in order to compute AT0, so reference evapotranspiration, and, for example, vapor pressure deficit, which is also related with the daily scheduling. But what are the critical issues? First of all, that we need on-farm weather station or data provided by public services or weather forecast services. It is recommended that there is a data integration from different sources. It is important, as also it has been highlighted, that the quality of data for the computation and the need of alternative models, because sometimes we have limited weather variables available. And the standardization of the weather sensor installation is positioning is a recurrent mistake. Sometimes in the field we find a very, very big mistakes in the correct positioning of the weather station. And last but not least, especially for fruit crops, there is the need to consider the effect of plastic or net covering on the microclimatic condition for the correct adjustment of AT0 VPD calculation. So this is an example of a weather station installed close to an orchard, and within the orchard, it is possible with the IoT nodes, for example, to monitor the microclimatic conditions in order to adjust the estimation according to this condition. Or we can try to understand the effect of plastic nets with measuring the photosynthetic active radiation below the nets, or the quality of the light below the nets. This is the first. The second step is to understand the crop growth, and so to assess the parameters, the crop-specific parameters that are needed to estimate the crop requirements. So, of course, there are a lot of things to consider if we move from the typical open field crops to the more complex orchards under cover. So the issues are related with the adaptation or calibration of crop and plot specific KC or KCB parameters. And so to have practical methods and tools to estimate the biometric parameters of the crops, to model canopy growth, to consider also the sensitivity to water stress of the different crops, and also to consider the presence of weeds and grassing, because they have a contribution to ATC. So this is what we have focused in our application, how to correct the KC curve as a function of parameters that can be measured in the field, or how to relate this curve with satellite indexes or phenological models. For example, we have used this approach to collect at field scale very, very easy data related, for example, of the fraction of canopy cover, the percentage of weed, the height of the crop, the presence of net, and we have developed a tool for the correction of the estimation of the KC. And this is, for example, the results for the prediction of kiwi fruit orchards, different kiwi fruit orchards in relation to the specific condition of each orchard. Or we can use image acquisition. For example, in this case, you see a stereo camera that is providing the estimation of leaf area or the volume of the canopy based on image analysis. So we can use remote sensing to understand what is the relationship between the vegetation index and the KC to be assessed at field scale. The result is to compute the crop evapotranspiration, and so in order to provide the daily crop water requirements, and we can also estimate a possible stress index, KS, on a daily basis. The KS can be, or the ATC and the KS can be compared with some measurements, for example, with thermal camera measurements, and we can compare the KS with the crop water stress index, or we can compare the ATC with some data provided by some proximal sensor. For example, this is a picture of electrochemical sensor that can be used to understand the water flux in the branches or the trunk of the tree. Okay. Third step is to consider the soil properties. So everything which is related with soil texture, hydrological properties, rooting depth, rooting density, in order to perform the soil water balance model. Normally, the soil water properties are calculated, we can consider standard values for soil type and textural classes. We can use hydrological analysis, which is very rare in reality, but normally pedotransfer functions are used for the estimation of the hydrological parameters of the soil. But sometimes if we compare what is the measurements done in the laboratory with the retention curve, with the analysis of the pedotransfer function, we can find very, very poor relationship for the total soil water holding capacity. At least we have this experience with some soils. In any case, based on the type of soil, we can compute a daily soil water balance considering the input and the output. So the software normally provides the evolution of the soil water depletion. And so we can understand day by day what is the condition of the storage. And we can compare, as we have done for the crop with the plant sensor, we can compare the soil water balance with the soil sensors in order to understand if our prediction is correct, or we are under or overestimating something. The problem is that if we use soil sensor, and normally some calibration curves are provided with the commercial sensors, but we have to take care that normally there could be an under or overestimation. So a field-specific calibration should be done of the soil sensors, but this is not done in reality. So this is a weak point of the use of this sensor. Or another idea could be, especially when we have shallow water table and capillary rise, to use some piezometers in order to understand if the shallow water table is rising or is below the root zone. And finally, we have to consider the type of irrigation system and some parameters related with this. For example, the dripper discharge, the estimation of wetted volume and irrigation efficiency, the way we integrate irrigation data, that could be manual or by sensor or automated. We can set different irrigation strategy also in relation to management constraints, and we should also consider the water quality issues because this affects a lot the irrigation scheduling. By considering these parameters, we can translate the daily crop water requirements in the effective timing or volume of water to be applied. And if we consider water quality parameters, beside understanding if there are some possible limitation from the agronomic point of view, our experience is that we have to consider these parameters also to adjust the soil water balance, and so to adjust the crop water requirements accordingly. Okay, so from our point of view, to manage DSS for irrigation in real environments is somehow complex because we have to consider all these parameters. So a good technician is needed to support the farmers for a good management of variables and data. Just a few examples of application. For example, this is a table grape orchard in southern Italy. You can see the wrong positioning of the station, the presence of net and plastic, the necessity to understand the VPD behind the nets. Frequently we have stony soils, which are very difficult to manage, to understand the hydrological parameters. There is the drip positioning is challenging somehow, and as well as the sensor positioning. And also there is the relationship between irrigation scheduling and fluid quality should be considered. This is an example of evapotranspiration simulated calculated for an orchard. This is the irrigation scheduling. This is the depletion during the season. This is the sensor behavior, and as you can see, there is a good correlation between the soil water balance and the sensing measured by different type of sensors. This is another example. So this is kiwi fruit in central Italy. You see again the bed positioning of the weather station, the presence, the white spacing in this case between rows, the different type of nets. The presence of double irrigation system in this case, the variable level of grassing below the canopy, also here the relationship with the fruit quality, the presence of drainage collectors, the shallow water table, and the relationship with some diseases that are affecting the crop. And this is an example of water balance with total water requirements of close to more than 4,000 cubic meters per hectare. You see the depletion curve, you see the data from the sensing in the soil. So just to close, there is a lot of need of research and development for those like us providing this kind of tools. So we cooperate with a lot of research institutes in Italy. We have a different project from the European to the local scale. And I give you just a few examples. In the Universe Water project, we are specializing the DSS to manage poor water quality, for example, coming from reclaimed wastewater or saline groundwater, by integrating different type of sensors that allow to monitor the quality of the water itself. In another project, which is called Demetra, we are specializing the software to consider environmental issues like the irrigation management in nitrate vulnerable zones, so to provide tools for the farmers in order to limit the nitrate leaching through a good, precise scheduling of irrigation and fertilization. In another project called AgriData KPI, we are computing environmental indicators like water and carbon footprint, which are related. And we do research and development also in collaboration directly with customers. For example, with Zespri, we are developing a DSS specialized for kiwi fruit orchard irrigation management. Or with Irritech, we are developing a smart app that, beside the irrigation scheduling, it is supporting the connection with the remote control system, also complex fertigation systems. So finally, some conclusions. In my opinion, digital technologies offer potential advantages to support real-time monitoring of crop status and planning of irrigation. The integration of different technical approaches, so modeling, sensor, satellite, remote control, allow for an improvement of the technical service and support. However, there are some major issues related with the quality and reliability of data, and including key parameters. And so from the technological standpoint, there is an increasing need of integration with automation and remote control system. Relevant topics, as you have seen, must be properly considered in the DSS development, like water quality, wastewater use, and environmental issues. And finally, for an effective and profitable use of these digital technologies, an appropriate organization at farm scale is required, together with a qualified technical service, always with boots on the ground. Okay? That's all.
Okay, thank you, Vito, for this interesting presentation. We did receive some questions. It is rather related to the first presentation, so I suggest we run through the questions, and then if in the meantime new questions show up for Vito, feel free to put them in the chat, and then we can handle them as well. So Dorina, I will ask you two questions. The first one is, if you have small plots which are owned by different people, different family members, can your devices or can the digital tools and the decision support systems also work fragmented, so on smaller pieces of land, so that you use the tool for fragmented land, or is that not possible?
Of course, it is possible, as our sensors are meant to be put in the location that you need the measurement. So you can use your system and sensors in the area that you want to measure the parameters. So there's no problem with small plots. You can use it everywhere that you want.
And if you would then apply automated irrigation, can your
Yes.
automated irrigation also be steered that it will then give water to a certain piece of land, not the whole area?
Yes, yes, that's a possibility. It can be arranged as the farmer wants.
Okay, yeah, okay, thank you. And then a second question, what type of sensors do you use for water quality, and do you also measure the nutrient loads in water?
So we do offer sensors for water quality and quantity. We have TDS sensors, we have pH sensors, we have for the asset quantity, yes. Yeah, so we do offer several for water quality and level meters. Yes. Did I cover your question?
Well, I met Casper last week, and I know he offers a platform to measure nitrate and phosphates, so I think he might be interested to interact with you to see if you can exchange on that. So Casper, welcome to complete the information sheet, and then yeah, we can see if this could be complementary.
Of course,
Okay.
of course.
These were the questions for you. Then we look to questions for Vito. Yeah, Vito, if you are not a researcher who should be, so I think this confirms that you are very well aware of the whole the whole technical background to irrigate and so on, but I don't see particular questions for the time being. So to the audience, welcome to ask other questions. Sorry, now there's one popping up. Are those DSS shown appropriate only for farm scale, or can they also be adopted at district scale?
The question is for me, Charlotte?
Yes, the question is for you.
Yeah. As I've mentioned in the beginning, we are applying the software also at district scale. So working, for example, with irrigation consortia. Of course, the type of users changes the type of analysis that we have to do, the data, the type of modeling that you can apply. But the answer is yes. Yeah.
Okay. So thank you. And then we move on to our next speaker. This is George. So George, you can start sharing your screen. Thank you.
Thank you.
You still need to put it in presenter mode.
Yes, I know. Hold on.
Yeah, okay, perfect.
Let me know if this is working. Can you see the presentation mode?
Yes.
All right. So greetings and thank you for the invitation, the opportunity to be part of this webinar. My name is Manassakis Georgios and I represent ICT Solutions, which is a Greek technology company specializing in the digital platforms and for smart and sustainable agriculture, water management, and infrastructure. Now, in this presentation, I will focus on how digital tools and decision support systems can help us manage water in agriculture more efficiently, and in particular, how we can assess the risk of using alternative water sources for irrigation. The solution that we'll use as a reference point is our agriculture platform, which is WeGrow, which you see on the slide. WeGrow is a part of a broader portfolio of Wings, and it supports different sectors. But today I will zoom in its role for field management, irrigation optimization, and safer water reuse. And as we go through the slides, I will connect the core functionalities of this platform with concrete examples of European projects that we deal with water reuse, risk assessment, and decision support for farmers and managers. So before going deeper into the decision support aspects, let me give you a quick snapshot of where WeGrow sits in the overall Wings ecosystem. So Wings develops a family of digital solutions that address different verticals. For environmental protection, we work with air quality and wildfire solutions under WeBreathe. For energy, we support monitoring and optimization through WeSense. For infrastructure and mobility, we have WeMove, and for water, we have WeSense Water Platform that focus on smart metering, leak detection, and network optimization. So on the agricultural side, we have WeGrow, which is for farming and aquaculture, and WeSupply for Industry 4.0 and logistics. Now, all these are connected through common building blocks, which is IoT, connectivity, cloud, AI, and user-facing decision support tools. And you may ask, why is this important to today's topic? Because when we talk about alternative water sources for irrigation, for example, treated wastewaters, blended surface and groundwater, desalinated water, we're not looking at a single field. What we try to do is we're looking at the interface between water network, treatment processes, and the farm. So having an integrated ecosystem allows us to bring data from all these layers into one DSS and to assess risk in a more holistic rather than in isolation. Okay, so let me now move to the core of WeGrow and its field management capabilities, which sit at the heart of the decision support. So WeGrow offers a detailed view of its farm or parcel, combining geospatial information, crop data, irrigation configuration, and sensor measurements. So on top of that, it supports different profiles. So what a farmer sees is different from what an agricultural consultant or a cooperative manager sees. But keep in mind that they all work under the same underlying data. So at field level, the platform supports monitoring of soil moisture, crop status, weather conditions, and farming operations, and then overlays this information with recommendations for irrigation, fertilization, and plant protection. For water-related decisions, this is crucial because the DSS can estimate how much water is needed, when it should be applied, and under which conditions it is safe to use an alternative source. So you can think of WeGrow as a front end where the farmer interacts with the system and the place where complex models and the risk assessments are translated into more simple, actionable suggestions, such as irrigate this field tomorrow with X millimeters of water from source A, or avoid using source B this week due to elevated risk indicators. So on the right side, you see some of the main platform features that support decision-making. So we have beneficiary card for each farm, where we store structural information about the crop type, varieties, planting dates, irrigation, infrastructure, and so on. Now, agricultural consultants have their own view, which allows them to monitor multiple farms, compare performance, and fine-tune the recommendations it should provide. The platform also includes a weather data tab and forum tab. The weather tab aggregates meteorological information that feeds directly into our models, while the forum tab is used to exchange practical feedback. For example, when a farmer observes anomalies in the crop or response behavior is not going okay with a particular water source, etc. Another key element is the carbon footprint and sustainability indicators, which are becoming increasingly important in policies and subsidies, in schemes for subsidies, especially in Greece. When we improve water efficiency, of course, and we choose a safer and more suitable sources for watering, we directly support lower energy use and somehow reduce the environmental impact. Finally, irrigation optimizations are calculated per parcel, okay? So taking into account not only water availability, but also the risks that are linked to salinity, nutrients, or potential contaminants. This is where the link with alternative water sources becomes very direct, and the DSS can include constraints and thresholds that reflect microbiological, chemical, toxicity limits, and adjust the recommendation strategy accordingly. So to provide meaningful irrigation and risk recommendation, of course, we need good data from the field, and this is where the sensors and monitoring play a central role. In WeGrow, we typically work with soil moisture sensors, which are installed at different depths to capture how water moves in the soil profile. This allows us to judge if the root zone is adequately applied or if the crop is under stress. And in parallel, we use weather stations that measure temperature, humidity, wind speed, precipitation, which, of course, as the previous speakers say, are key drivers for evapotranspiration and water demand. So we can also integrate soil fertility sensors that provide pH and NPK measurements, whether this could be online or through periodic laboratory analysis. And these are highly relevant when using alternative water sources because such source may introduce extra nutrients or salts into the system. Now, all this information feeds into the monitoring and alert system. The DSS can issue notifications when critical thresholds are exceeded. For instance, if soil moisture falls below a safe limit, if salinity is building up, or conditions favor different pathogens. In water reuse context now, this means that the system does not just say irrigate or don't irrigate, but irrigate safely under the right conditions and with the right source and volume. Of course, behind the scenes, the technical backbone that enables all this is our interoperable data acquisition and communication platform based on Wings Gateway. Now, the gateway is the interface, can interface with a very wide range of meters and sensors with water quality probes, electricity meters, soil and weather sensors, pumps, valves, and other controllers. And on the communication side, it supports multiple network technologies, GPRS, 4G, 5G, NB-IoT, LoRa, Wi-Fi, and a range of protocols, including MQTT. Now, why is this important for a DSS on alternative water sources? It's because in any pilot sites and real-world system, data lives in silos. So a treatment plant has its own SCADA. The irrigation network has another system. Farmers may use separate sensors or logbooks. So the gateway layer allows us to bring these heterogeneous streams together into one platform. Additionally, the gateway supports edge computing. This means that some basic intelligence can run locally. For example, if water quality sensor at the outlet of a treatment unit detects some values that are above a risk threshold, the gateway can trigger more frequent measurements or set immediately an alert, or even prevent irrigation in real time, depending on the configuration that we have set. In simple terms, this means that we can implement a multiple-layer risk management approach, so some safeguards at the edge and more comprehensive risk assessment and DSS logic in the cloud. And all of this connected to the farmer's interface. Okay, so on this slide, you see weather and soil moisture prediction components, which are key ingredients, of course, for the decision support processes. So through a weather API, we retrieve short-term forecasts for temperature, rainfall, radiation, and other relevant variables. So these forecasts are then combined with soil moisture measurements and crop parameters inside the prediction model that estimates how soil moisture will evolve in the coming days. So the AI model produces a 4 to 7 day forecast for soil moisture for the different depths in the profile. And this is done in an hourly time step. So using this forecast, we can design an irrigation plan that keeps soil moisture within optimal band, which is defined by field capacity at the upper end and readily available water at the lower end. And when alternative water sources are part of the system, for example, treated or blended water, the same optimization algorithm can take into account additional constraints, which may include allowable salinity, limits of the load of certain ions, restriction on irrigation during specific crop stages, when sensitivity is higher. And we can say that instead of a generic recommendation, the DSS can then provide information like, given the forecast and the soil status, the quality of the available water sources, the safest and more, let's say, efficient strategy is to irrigate this field on these specific days using a combination of sources at specific volumes. And this is where, of course, classical irrigation scheduling meets risk-aware decision support. Okay, so let me now connect these building blocks to a concrete example that focuses explicitly on risk assessment for alternative water sources. And this is, of course, the work that is carried out in the NINFA project. So in NINFA, the objective is to correlate measurable parameters, for example, from sensors or laboratory analysis, with indicators of microbiological risk, toxicity risk, and chemical risk. So we look at parameters such as turbidity, conductivity, nutrients, specific contaminants, and we relate them to health and environmental risk categories. So the DSS aggregates this information and produces a risk assessment that is visualized for the user. And usually this is done through alarms and color-coded warnings. So for instance, green might indicate that water is suitable for irrigation under given conditions. Yellow might suggest caution or additional treatment that is needed. And the red signals that irrigation should be avoided. What makes this approach powerful is that the DSS not only flags the risk, but can also act on decision variables related to water treatment technologies. And it can suggest operating a particular treatment step more intensively, mixing sources with different proportions always, or temporarily switching from one source to an alternative source. And in practical terms, this means that a farmer or a water manager does not need to interpret all the raw lab results and sensor readings. Instead, they receive clear risk-based recommendations that link the water quality, the treatment options, and the irrigation decisions. And this is exactly what the type of support that we need if we want to scale up and the safely use of treated wastewater and other non-conventional sources in agriculture. Okay, lastly, another example is the Univer Water initiative, which was also mentioned by the previous speaker, which aims to build a universal DSS platform to support water use and irrigation decision. And this is to be done across multiple countries and pilot sites. So the platform that is developed is designed to help farmers and managers answer very practical questions. These questions could be like, how much should I irrigate? So should I fertilize or spray? Can I mix or reuse different water sources? How can I prevent salinity from building up? And to do this, the DSS integrates data and models from IRIS, Italian and Greek pilots. It is operating in different climatic, regulatory, and agronomic contexts, as you can understand. This forces the platform to be flexible enough to handle various types of alternative water sources, reclaimed waters, including drainage water or desalinated water, but also maintaining a common risk assessment framework. So one of the key goals is to create the reusable DSS architecture, where local models and thresholds can be plugged into a common core and then to be adapted into new regions. From the user perspective, this enables a consistent experience. Whether they are in Ireland, Italy, or Greece, they can work with a tool that combines water quantity, water quality, and agronomic risk into integrated recommendations. Taken together, I think Nympha and Universe Water show how the same underlying technologies, which is sensors, gateways, cloud analytics, and WeGrow style interfaces can be specialized to deal with water reuse risk and not only with standard irrigation scheduling. I think this sums up my presentation, and we can all have time for some questions.
Yes, okay. Thank you, George. Let's have a look in the chat if there are questions already. I don't see them yet, so people feel free to ask your question to George if you have one. Okay, then we move on to the last speaker, which is myself. I will start sharing my screen now. Here we are. My presentation is about a tool that I want to present to you. The tool is called Water Radar. I will give an online live demo about the tool. I hope technology will be with me today. In case you see things are not moving, please can somebody tell me, because I also have a plan B and I prepared some slides just in case. So the Water Radar is actually a tool that has been developed in Flanders to act as a matching tool between water supply of alternative water sources and water demand for alternative water sources. So our three former speakers were from the south of Europe, where they face already for several years drought and where they already use in a very smart way alternative water sources, but also in the north of Europe, in Belgium, we are more and more facing water scarcity, so we need to be prepared and develop tools to act upon that. So what you see here, if I zoom out, you see, of course, Europe, this is Belgium, and here you see Flanders. If I zoom in on the map, you can see Flanders and you can see all kind of small blue dots and yellow parts also. The blue dots are actually agricultural fields, and the intensity of the blue indicates the intensity of the water needed for irrigation. So when you see the gray parts are just residential areas, yellow parts are agricultural fields without need for water, and then the blue parcels are irrigated parcels. The water demand, what you see here, is a theoretical calculation. It is calculated based on the crop that is grown there and with a theoretical irrigation that would be supplied in normal meteorologic conditions. The calculation is always based on the year before, because we have these, the farmers need to report their parcels every year. At the end of the year, this information is public, and based on that public information, we can create the map. But the map is actually always showing the irrigation demand of the year before. But as we know, crop rotation and so on, farmers will not have parcels very far away. So what you see here is more or less the, let's say the hotspots of water demands in Flanders are situated here, and then this zone, and then this zone. Okay, so we want to match now the water supply, and we want to help farmers to find alternative sources. So then you can go on the tool, and sorry, I see it is still in Dutch. I will now switch it in English so that you understand the wordings. So we go to the tab Scenarios and Maps. What we see is the water need for 2024, and now I go to the tab Supply Scenarios. And then I can choose for two alternative water sources, either the treated waste from water from a municipal wastewater treatment plant or the treated wastewater from an industrial industry, and we actually limit ourselves to agri-food companies. When I click on all suppliers, you can see that the map shows all kind of dots where there are alternative water sources available. And then I need to give a location. If I am the farmer, I give my location where I live, and then you can see the water supply in the area. For instance, if I go to my hometown, sorry, it was showing up here. So the tool takes you to the city center, and then you can see that all kinds of alternative water sources are showing up. When it's round, when it's a circle, then it's municipal wastewater. When it's a square, it's a food company. So, for instance, if this is my parcel, I can click on it. Then I can see here, so in this parcel, the crop type is potatoes. I can see what would be the irrigation need for the whole parcel if I would need to irrigate 125 millimeters. And then I see also where do I find alternative water sources in the neighborhood. So I get a listing, and for each location, you can see the distance from your parcel, the cubic meter of water available per day, and you also get an idea of the chloride concentration, because you don't want to have too salty water not to hamper the growth of the crops. So this gives you an idea. Of course, here you see the radius a farmer doesn't want to go very far, so you may wish to lower the radius. So if I put it on 2 kilometers, then you get a circle, but unfortunately there's no alternative water supply within a perimeter of 2 kilometers. Let's put it on 4 kilometers, and then they show up again. There are a few. You might also notice that there are different colors. There are red locations, but there are also green locations. You know, we have the water reuse directive. So when farmers want to use wastewater, they need to have a permit. I'm sorry, somebody is making some coffee here. So, but they need to have a permit to be able to use the water for irrigation. And the locations which are green are the ones who already have this permit in place. So for the time being, these are then the only locations where a farmer can go to get some water. However, the tool is mainly intended to set up a dialogue between a water supplier and a farmer who needs water. So it is not because sometimes the colors are still red that it cannot turn green. So we actually stimulate then farmers to reach out, to have a discussion, and to see if collaboration and sustainable water exchange would be possible. Of course, we are not in favor to have water transported over the road. So in the ideal world, they really set up a sustainable exchange via an underground piping network, for instance. But at least this tool gives you then a first idea on how this could work. What else can I tell you? This is now from the side of the farmer. So the farmer knows his parcels and he looks for where in the neighborhood do I find supply. You can also use this tool from the other way around. When you are a supplier, you can also actually look where is there a water need in my immediate neighborhood. So then you click actually on the dot where there is the supplier. However, I have to say, I also tried it yesterday and this was then not working. But what you see here is actually the location with all the contact details. And normally, but it's not showing up now, but the tool would tell you here in an area of 10 kilometers, what is the irrigation need and what are the most predominant crop types that are in need of water. You can also lower the radius then, and this actually also informs water suppliers if they say, okay, I have wastewater which I discharge, but perhaps people in the neighborhood, farmers in the neighborhood can use it, then in this way, you can actually investigate, is there a water need in my neighborhood? And then you can also set up the dialogue. So this is actually the tool. I hope it is clear. I go back in the general Zoom. Yes, and I will look in the chat if there are questions. So, okay, I think the question which I see here is already for myself. Did you consider other quality parameters except for chloride, for example, the PFAS concentrations in industrial or sewage effluent, which can be high? Okay, so in the tool, we only show very limited amount of water quality parameters, actually only the chlorides, because the first thing we want to check is the water from the macronutrient level okay for irrigation use. This tool was created before there was the water reuse directive implemented and translated in Flanders. So we were not aware yet then of all these other pollutants. So today things have changed a bit. So when you want to reuse the water, you need to do a risk assessment. And at that time, we need to analyze the water that will be used for irrigation. And we need to take into account, for instance, PFAS and other micropollutants and make the assessment if it's safe to use or not, if it's below the thresholds or not. So we do not show it. Because also we do not have this information publicly available, but we do take it into account when a match has been made and when people really look for a real collaboration. Okay. Sorry, I'm also looking to the questions. How did you map the farming land? Was there a database for them already? Yes, we do have that database. So in Belgium and I think also in the other countries in Europe, the farmers need to report their crop type. So we have land use maps, and that we start from these land use maps. And then how do we see the transport from the industry to the field? So today we do have some irrigation networks already in place. Then the system goes as follows, that the treated wastewater is stored in a buffer basin, and there is an underground piping network installed which distributes the treated wastewater to the different parcels. That's one option. The other option is that the farmers still come with their tractor and with their water bin that they have, and then they can pump. It's about 20 cubic meters, and then they drive up and down to their fields to irrigate, which is not the most sustainable way, I know, but in times of crisis, you do the best you can. Okay, then another question. Have also other suppliers of grey water, like Indus, Ecopack, or other, taken into account? Yeah, so actually anybody who has water available can be shown on the tool. In case you are interested to do so, you need to contact the Vito people, because now the data from the food industry, they are shown automatically because we get this data from the Environmental Agency database. But ad hoc, we can also add other suppliers. For instance, we have a drinking water company, and at 5 locations, they regularly need to do kind of backwashing processes, and that backwash water, which is actually very safe drinking water, is also offered to farmers. So at these locations, the water supply is also shown. So anybody who's a supplier can be registered if they are open to it. Okay, these were the questions for me. I don't know if there are other more general questions. Do you have a determined price for the wastewater? Okay. In Flanders, the municipal wastewater is treated by one water utility, which is called Aquafin. When they provide water to the farmers, they ask just to deliver the water. I'm not too sure about the price out loud, but in former days it was said to be 0.60 euro for 1 cubic meter of water, not taking into account the price for instance, further treatment, disinfection, or the pumping of the water to the location. When it comes to the industrial wastewater, to the best of my knowledge, the companies don't really ask a price for the wastewater because they discharge it anyway. But of course the farmers need to pay for the pumping and the infrastructure. And we have such an irrigation network in place, and there the price is 0.9 euros per square meter of water. Perhaps another thing worth to mention is that our environment agency wants to stimulate the reuse of treated wastewater. So when companies provide or give water to farmers, they do not need to pay levies on that volume of water that is provided. So it's a kind of financial bonus if they offer the water for reuse. Okay, sorry, I'm talking a lot. Is there a demo version of the programs shown today, for example, for students to familiarize? Is there a catalog that could be sent out after the webinar? So perhaps that's a question also to the other speakers. We have now seen different systems, the system of AGENSO, the system of Blue Leaf, and then the system of Wings. I don't know, are one of these systems available for demo? Are the demo versions of the systems available? Other speakers, can you react on that?
Charlotte, I think that who is interested can send an email. You can provide our contact, and we can see case by case. It must be open an account on the web version, and they can use it.
Okay. So
just a point, Charlotte, sorry. I see some raised hands in the chat, so I don't know if they can speak or they have only to write. There are two people with raised hands.
Sorry, I have not seen that. I think we still have some time. If people want to ask a question out loud, this is fine for me. Then you can turn on your mic and ask your question. I just want to conclude what Vito said. So after the presentation, so we will definitely share the slides, and we will then also indeed share the contact details of the speakers. So in case you want to bilaterally connect and have follow-up questions, feel free to contact them directly. Okay, so the raised hands, please, if you want to ask a question, go ahead. No, I have not. I don't see it. And then, okay, then I just see one last question. Is there a similar system in place in Wallonia? I think for the water radar, no, not yet. It's not in place. No. Okay. I do not see any further questions. There is nobody unmuting for a question. So then I think we can conclude here. Thanks again. Thanks a lot to all the speakers for today. Thank you to the audience for listening. I hope you have been inspired for your ongoing work. And then yeah, let's stay in touch via email, and you will get, as I said, the slides then afterwards. Thank you, everybody.
Thank you.
Thank you.
Thank you.